Thermodynamics by Lorena Diostato. I'm in 2B. So first we're going to look at the first and second laws of thermodynamics. And so the first law says that the law of conservation of energy, that is the total energy of an isolated system, will remain constant. So basically what this is saying is a very standard energy cannot be created or destroyed, it's just transformed. And when you look at the second law, it's that systems have an overall tendency to increase in entropy. And entropy is what I would call disorder. And we're going to get a bit into entropy in a little bit. So what is enthalpy? So enthalpy is the total heat content of a system. And that is going to be equal to the internal energy of a system plus the product of pressure and volume. So basically, it's the amount of heat in the system. It could be endothermic, exothermic, so positive or negative. So what is entropy? Again, we're going to have the unavailability of a system's thermal energy for conversion into mechanical work. So that is going to be the degree of disorder or randomness in the system. So the more disordered a system is, the greater entropy it has. The more ordered it is, the less entropy it has. So basically what that means is something you can observe in your daily life. So if you look at your desk, you may have it super neat right now, but if you give it a few times, it's eventually going to look awfully messy. So that's just naturally the way things go towards disorder. So then what is free energy? So free energy is going to be the capacity of a system to do work. So when you put it together, you get this equation where delta G, that's your free energy, is equal to delta H, that's your enthalpy, minus temperature in Kelvin times delta S, which is your entropy. So you put it all together and you're going to be able to use this equation for various situations. So what is the significance of delta G? So if your delta G is negative, it means that the reaction is spontaneous. And if delta G is 0, then the system is at equilibrium. So obviously if the delta G is positive, then the reaction is not spontaneous. So are there any trends that you can see with your entropy, enthalpy, and your free energy? Why, yes, there are. So if your delta H is positive, so if your enthalpy is positive, and your delta S is positive, so your entropy is positive, you're going to have a spontaneous reaction at high temperatures only. And that's going to be because you have an endothermic reaction and you have a lot of disorder. So you are going to have the possibility of a spontaneous reaction, but only if it occurs at high temperatures. If your delta H is positive, so if your enthalpy is positive, so it's endothermic, and if your delta H is negative, so if your disorder is decreasing, your entropy is decreasing, then it will never be spontaneous because those are both unfavorable things. But if your enthalpy is negative, so it's exothermic, your reaction is exothermic, and your delta S is positive, so it's a lot of disorder, then it will always be spontaneous because those are the two requirements for a spontaneous reaction in all cases. We love disorder, we love exothermic reactions. But if your delta H is negative, so if you have an exothermic reaction, and your delta S is negative, so you have a lot more order than disorder, then it's only going to be spontaneous at low temperatures. And these are trends you could probably reason out or you could memorize, up to you. So let's work out a problem. So calculate the free energy if your enthalpy is 34 kilojoules per mole and your entropy is 5,000 joules per Kelvin moles at 36 degrees Celsius. So we have that equation, delta G is equal to delta H minus T delta S. So it's going to be a plugging in of numbers. So 34 minus 36 plus 273, so we can get that temperature in Kelvin, times 5,000 divided by 1,000 because you want to transform those joules into kilojoules for your entropy. And you're going to get negative 1,511 kilojoules per mole. That's going to be your free energy in the system. So was the previous reaction spontaneous? Well, let's look at that again. We said negative 1,511. So yes, your delta G was negative, therefore your reaction was negative and spontaneous. If delta G is equal to 56 kilojoules per mole and delta H is equal to 623 kilojoules per mole at the temperature of 25 degrees Celsius, then what is entropy equal to in joules? Not kilojoules, but joules. So delta G is equal to delta H minus T delta S. So let's plug in numbers again. We have 56, that's going to be our delta G, is equal to 623 minus 25 plus 273, because we want to get that temperature in Kelvin, times your delta S. So what do we do first? We subtract the 623 over to the 56. We divide that by negative 25 plus 273, and you're going to get that to solve for delta S. And so when we calculate that, we get delta S is equal to negative 1.903 kilojoules per kmol, or negative 1,903 joules per kilomole, because they wanted it in joules. Remember that? And so this negative entropy value means that there's a lot more order, because remember, greater entropy means greater disorder, so lesser entropy means more order. So given the following entropy values and enthalpy values, calculate delta G at 25 degrees Celsius. Okay, so this is all going to be given to you, and so let's look at it. So silver chloride is equal to silver ion plus chlorine ion. So our delta H in kilojoules per mole for silver ion is 105.79. For silver chloride, it's going to be negative 127.01. And for chlorine ion, it's going to be negative 167.08. I'm sorry. Our entropy, our delta S, is going to be equal to joules per Kelvin mole. That's going to be equal to a silver ion of 72.7, a silver chloride at 96.2, and a chlorine ion at 56.5. And so you may be asking yourselves, which of the following do you pick? Well, the answer is all of them. Because the way this works is that you take the sum of the products and you subtract that, you subtract the reactants from that, sum of the reactants. And thankfully here we only have one reactant, so we just need to add up the products and then subtract the reactants of that. And you do that for each one. And keep a note that you could do this for free energy values themselves as well, if you're given those. Okay, so let's plug in these numbers. So we're going to take our silver ion and our chlorine ion, and we're going to add those together, keeping in mind that a negative value needs to be included. You can add parentheses, or you could just simply change it to subtraction. Either works. So 105.79 minus 167.08 plus 127.01 is going to be equal to 65.72 kilojoules per mole. And now we look at our entropy. That's going to be 72.7 plus 56.5 minus 96.2, and that's going to be 33 joules per Kelvin mole. And one thing to keep note of is, say that your silver or your silver chloride or your chlorine had a coefficient. The way we factor that in is you just multiply their entropy or enthalpy or free energy values with that coefficient, because it's the number of moles. So you would just have to multiply that in. Luckily here we don't have any coefficients, so we could just multiply by 1, which basically means you don't have to do anything. Okay, so here are those values once again, and we're going to calculate delta G at 25 degrees Celsius. So here we have that handy dandy equation of delta G equals delta H minus T delta S. So delta G is going to be equal to that enthalpy value we calculated earlier of 65.72 kilojoules per mole, minus 25 plus 273 to get your temperature in Kelvin, times 33 over 1,000, and again we're dividing by 1,000 because our original value was in joules and we want that to be in kilojoules. And so we're going to get 55.87 kilojoules per mole. Okay, so thank you for your time. I hope that was helpful and that you took something away from this unit of thermodynamics.